So 5.2 takes a look at how we use the first derivative to determine where a function is increasing or decreasing and where it may have maximum or minimum points. So let's take a look at this picture here. Obviously we can see where it has maximum, minimum points, where it's going up and down, but I think what we want to highlight here is really more along the lines of exactly how would I know? How would I know that this is going to happen? So let's start with this, right? Notice that every time the graph is going up, that any tangent line that I draw, no matter where, happens to be positive. And so if we make that connection to the fact that the first derivative is positive, then that tells us that the function itself is increasing when that happens. Likewise, when you see those tangent lines start to become negative, right? That means our slope or our derivative is negative, and that means that the function itself must be decreasing. And then on rare occasions, every once in a while, you will have a situation where the derivative is 0, and that just means that the function is constant. So, for instance, if we just stay color-coded here for a minute, right? If the function goes up and then goes across and then goes, let's say, back down or something, that would be all three of those cases coming together. So the key is, well, how do I know that these things are going to happen? And so the maximums and the minimums are a clue as well, because see, the maximums and minimums cannot occur unless the derivative changes from positive to negative or negative to positive. So let's look at what we call those special points. Call them critical values. So a critical value is where the derivative, there you go, is either 0 or in some cases could be where it's undefined. And like we said before, if the derivative of a function changes from positive to negative, you go back to that picture we had before, then there's what we call a relative maximum. And that would mean that the function had to go from up increasing to down decreasing. Now, if a derivative goes from negative to positive, then there must be what we call a relative min, because the function went from down to up, decreasing to increasing. So really the best thing we can do at this point is look at two examples. So there are a couple examples in the note packet. I'm going to specifically look at 1 and then 4. So let's start with example 1. So obviously if everything that we're talking about right now is based on the derivative, then we need to find the derivative. So we'll start with that. So 3x squared minus 12x plus 9. And we saw before that a critical value is where the derivative is equal to 0 or doesn't exist, is undefined. So that being the case, this is a polynomial here, so that's never going to be undefined. So we really just have to find places where this thing is equal to 0. So just if we do a little factoring here, x squared minus 4x plus 3. Keep factoring here. And solve this, we will now figure out, right, that we have critical values at x equals 3 and x equals 1. This right here is not a critical value because it doesn't equal 0. 3 doesn't equal 0, it doesn't make any sense, right? So now the only question that remains is, all right, we found this critical values. What does that mean? Well, maximums and minimums can only occur at critical values. The problem is we don't know if the function is going from up to down or down to up. So the only way to figure that out is to test. What does it mean? Well, we have to test values of the derivative around our critical values. So I'm going to place those on a number line real quick, and then I'm going to do things like this. I'm going to say, let me pick we'll call it a test value in this interval. Let's say 0. And I'm going to find f prime of 0. And so when I come all the way back up here, or even here, any one of those are fine, right? I'm basically looking for what the value of the derivative is at 0. And I find out that it winds up that the derivative is positive. Now, if this is the case, this is really important, because what that means is f itself must be going up during that interval. So now how about if I pick a value like 2, test value of 2, right? Plug that thing back in. Well, what I'm going to find out is I get a negative for the derivative. And what that means is that the function itself must be going down. And then if I picked, let's say, a test value of like 10 out here in this interval and plugged it back in the derivative, what you're going to find out is that you actually wind up getting a positive again. So therefore, the function now is going up. So this first example asked us to tell them where the function was increasing, where is it decreasing, where do we have a max or min, and look, something important here. Right here at 1, we must have a max, and right here at 3, we must have a min. How do I know that? Because I see the function's behavior going from increasing to decreasing, because its derivative went from positive to negative. So these are the details I'm looking for. So to sum up, let's put it all together here, right in this little box. Okay, the function is increasing from negative infinity to 1, and then again 3 to infinity, decreasing from 1 to 3, and we've already pointed out where it has a max at 1, and a min at 3. Okay, so let's do one more example. Now, with number 4, go ahead and do the derivative if you haven't already. So y prime equals 10 thirds x to the 2 thirds minus 10 thirds x to the negative 1 third. And if we were to try to set this thing equal to 0 or undefined, a couple things here. It's a little tricky, so we're going to factor out, and just like any other GCF factoring, we take out the lower of the exponents. So 10 thirds x to the technically negative 1 third, and that leaves us with x minus 1. And maybe we want to write this just a tad bit differently. 10 over 3 cube root of x times x minus 1. Here's why this example is important. In the previous example, we said, let's go find some critical values, and we focused an awful lot on where the derivative was 0. Well, so here that would be at x equals 1. However, the derivative is undefined at 0, so I have to include that when I'm testing here. And what you'll see me do a lot of times is I'll just put like a little bit of a dotted line or a box or something around the undefined point, so I understand that the point itself is not defined, so don't try to plug that number in or do anything with it really in the derivative. So again, we continue to test, we continue to do our thing. So I'm testing again, just a reminder, I'm testing f prime. So if I put a number in that is a little bit lower than 0, negative 1, negative 10, right, I'm going to get the cube root of a negative, which is negative. I'm going to get a negative in parentheses here, so by and large that's a positive, which means the function itself is going up. Now if I put a half in, cube root of a half is positive, but 1/2 minus 1 is negative, so I get a negative here, indicating the function's going down. And then if I put a positive number in, I get all positive, functions going up. And here's where people make their mistake. The only extrema we have here is at 1 we have a min. We can't have a max at 0 because the point well, actually, no, we could have a max of 0. It's just not something that I was anticipating there. So we just had to watch out. We would have missed that, is what I was trying to say. We would have missed that if we did not catch it as a critical value over here. I think what I was thinking here is if we didn't have a defined point up here for the function at 0, then we couldn't have a max. So hope this has been helpful. And of course, as always, if you have any questions, let me know.